Hey everyone, let's continue with our series on solving differential equations. In this video, we are going to focus on separable first-order differential equations, and the form of separable differential equations is dy over dx equals f of x times g of y. Notice that in the right-hand side, we have here a product of the function of x and another function of y. We cannot solve this equation by direct integration because this right-hand side depends both on x and the unknown function y. And differential equations that look like this are called separable differential equations. Now let's take a look at some examples of separable differential equations. dy over dx equals xy squared is an example because we have here the product of x and y squared, which is our f of x and g of y. Another example is dy over dx equals the product of sine of x times cosine of y. Again, our f of x is sine of x, our g of y is cosine of y. Here's another example. dy over dx equals x over y squared. Now, this fraction can always be rewritten as product by rewriting the denominator y squared as 1 over y squared. And so the product here is x times 1 over y squared. Another example is dy over dx equals sine of x over cosine of y. Again, we can write this quotient sine of x over cosine of y as sine of x times 1 over cosine of y. If these are examples of separable differential equations, let's have also examples of those that cannot be solved using separation of variables. Here is an example. dy over dx equals x plus y. The right side cannot be written as f of x times g of x. Another example is dy over dx equals x y squared plus 1, again because the right side cannot be written as the product of two functions, f of x and g of y. Finally, dy over dx equals the logarithm of the product x times y cannot also be solved using separation of variables. The reason is the logarithm of the product of x times y is equal to the sum of the logarithms log of x plus log of y, and these two functions are not product of two functions. Rather, they are sum of two logarithmic functions. Now at this point, let's solve some differential equations that can be solved using separation of variables. Let's say our equation is dy over dx equals x squared over y is greater than 0. When I say we want to solve this differential equation, we are solving for that function y of x that will satisfy this given differential equation. So how are we going to solve this? The idea behind separation of variables is to gather together in one side of the equation those variables that are the same. Notice that you have here dy and you have here y. At the right side, you have x squared, and at the left side, you have dx. Now, the problem here is dy over dx is technically not a fraction. But in the separation of variables, the convenient way of solving this is to consider dy as the numerator and dx as the denominator. But before that, let's multiply both sides of this equation by y. So we have y times dy over dx equals y times x squared over y. And y divided by y is 1. So we have y times dy over dx equals x squared. Next, let's take the integral of both sides of this equation to have the integral of y dy over dx equals the integral of x squared dx. So we integrate both sides of the equation with respect to the variable x. Now this part here can be simplified using u substitution, and that will result to the antiderivative of y dy equals the antiderivative of x squared dx. Notice now that we have here y dy, and at the right side we have x squared dx. Both are y and both are x at the right side. And if you go back to the given original equation, it looks like you just cross multiply y times dy x squared times dx. And that is the convenient way of thinking about this separation of variables. Now, simplifying this, the antiderivative of y dy is y squared over 2 plus certain constant c sub 1. We use c sub 1 because there's another constant here also at the right side. So the right side becomes x cubed over 3 plus another arbitrary constant c sub 2. Now, if we let c sub 2 minus c sub 1 be equal to another arbitrary constant c, this can now be simplified as y squared over 2 equals x cubed over 3 plus the difference of c sub 2 minus c sub 1 is c. Then simplifying further, this becomes y squared equals 2 times x cubed over 3 plus c. Then let's erase this portion now. Solving now for y, we have y equals plus or minus the square root of 2 times x cubed over 3 plus c. Now, since it is given that y is greater than 0, then we'll disregard the negative sign here. We can now simplify this as y equals the positive square root of 2x cubed over 3 plus 2c. But since this c is just any arbitrary constant, we can also replace this 2 times small c with just another notation for that arbitrary constant. And let's use the variable capital C for the constant. So this is now simplified as 2x cubed over 3 plus some arbitrary constant, capital C. This is now the general solution to this given differential equation dy over dx equals x squared over y, solved using separation of variables. We'll have more examples in our next video. Bye for now.